This is the lecture we did on Monday, April 5th about acids, bases, and pH to fill in the lecture notes. So because it's a video, I may not slow down. I'm going to try and go fast. So all of the fill-in words are these dark blue ones. There are some there are some times where you might have to pick out something, or there's an extra blue word, or the color changes to red and green. But for the most part, look for colors to fill in the pieces. So we have an acid and we have a base. The acid is a proton donor, and the H plus is a proton because H has an electron and a proton and no neutrons. And so by removing the electron to make a positive charge, we're left with a proton. So that's the term proton. Actually, the proton is so reactive that in an aqueous solution, and almost all solutions that are reactive use water, H3O is the species that carries the H plus around for the acid. But we'll be using H plus and H3O interchangeably throughout this lecture. So acids are proton donors and often have H's at the beginning. Not always, and they're not the only things that have H's at the beginning. H2O, H2O2 are common examples, water and hydrogen peroxide with H's at the beginning. But in order to indicate an acid, typically you'll see an H in front to indicate an acid for that H plus that's causing the reaction. Bases form hydroxide in solution. So this OH is the basic part. They're defined as proton acceptors. Sometimes it'll be this that'll be the proton acceptor, and sometimes it'll be something else. Here's some examples. Here's some with the OH, the hydroxide, NaOH and CaOH. Ammonia, NH3, is a very common example of a base. So are the carbonates, sodium hydrogen carbonate, which is baking soda, and sodium carbonate, which is washing soda, common bases. When an acid donates an H, as you're seeing here, this H is leaving the Cl. It is going to be accepted by this OH, and so now we make water, the molecule water. Meanwhile, the sodium, which was in front for sodium hydroxide, and the Cl, which was in the rear for HCl, are put together in an ionic compound called a salt. A salt is a ionic compound formed by the reaction of an acid and a base, the proton donor and the proton acceptor. We can classify acids and bases as strong or weak, depending on whether they completely separate or whether they partially break apart or dissociate. For example, here's a strong, if we take a strong acid, every single molecule will separate in water to make H plus or H3O. That should be subscripted. Whereas the weak one, most of them will be molecules of the acid, and only a few will break apart to give the H plus. If I model that, it looks like this. For a strong acid, there will be no molecules of HCl in it. They'll all be separated between H and Cl. For weak, almost everything will be a molecule of HF, and few of them will be broken up into the ionic pieces, H plus and F minus. So our terminology for strong is an acid that separates completely when in solution, and our terminology for weak is that most of the molecules have remained together, and only a few of them have the reactive H plus available for reaction. We have the classification dilute and concentrated. Strong and concentrated are commonly interchanged in the English language. So if you go get a concentrated cleaning product, you're expecting it to be strong. So you may say, go get me something really strong to clean this with. and somebody may pick up something concentrated. But in this case, for chemistry, we want to use the word strong to indicate this separation of the molecule. And we want dilute to indicate that there's not very many of them in my aqueous or water solution. If it was weak, dilute would mean I have very few, and weak would mean most of them are still connected as a molecule, and only a few are actually separated into the reactive H plus and the anion of the salt, A minus. If it's concentrated, we just have more inside the same volume. Strong, completely separated, and weak, a lot of HAs all around and very few separated molecules. So that's the difference between concentrated and strong in terms of solutions, weak and dilute in terms of acidic solutions. Those solutions can conduct electricity if they have ions, and because strong acids and bases separate completely, they will strongly conduct. But weak acids with mostly molecules will only weakly conduct because they don't have very many ions at all. This makes conductivity a good test of acids and bases. So if you know a solution is an acid base and you test it with conductivity, you're likely to know that it's a strong acid with a strong conductivity, or a weak acid if it has a weak conductivity. However, it is possible to have strongly conductive solutions that are not acidic, like a saltwater solution. It's also possible to completely dilute a strong acid or base enough so most of the molecules are water and there's only a few ions of the acid available. So it's a good test, but not a definitive test of strong acids versus weak acids. Acids with high concentration react vigorously. If you poured a strong acid into water, it would react vigorously. It would heat up the water. The water would actually be able to boil if you continue to pour in your acid, and then it would splatter. This has been the cause of many holes inside lab coats. It's very dangerous, actually. Moreover, weak acids have small concentrations of either, depending on how you want to say it, H plus or more correctly, the hydronium ion, H3O plus, than strong acids of the same molarity. So what that means is that, I got to go back a little bit. If these two solutions were the same molarity, let's say 0.4, this has a molarity of 0.4 H plus, as well as a molarity of the acid, but this has a molarity of 0.4 of the acid, because there's 0.4 of the HAs, but the number of H pluses is only 0.1. So 0.4 versus 0.1. So when I talk about weak acids having a smaller concentration of H plus, it just means they have not separated, even though I put the same number of acid molecules into the aqueous solution. pH is providing a measurement of acidity that we can use to talk about acids and bases. When we talked about ocean acidification, we used pH both for graphing carbon dioxide versus the pH of the ocean, and where is the pH of the ocean, 8.1, versus where is the pH of strong bases and strong acids. To get the pH, we want to take the negative log of bracket H plus bracket, and that means the molarity of H plus or H3O plus. Remember, they're synonymous. In this graph, we have a couple things I'd like you to pay attention to. One, H plus is greater than OH. That means that here I have a lot of H plus. We can imagine this is a bar graph, and I have very little tiny bit of OH up here. And then here in the bar graph, it goes down, and it goes down, and it goes to imperceptibly small when you end up with a large amount of stuff. And so this, where we have lots of H plus, this is my acid side, which has both low pHs and high amounts of H+. On the other hand, if I have lots of H+ and lots of hydroxide and a little bit of H+, then the bar graph is big for OH and gets small for OH down here. This is my base, which has a pH of high numbers and a large amount of OH. We could also pay attention to the POH here and here for the acid and the base. And finally, what if I was exactly in the middle? If I was exactly in the middle of 0 and 14, I'd be at 7, and that would be neutral. So I have a lot of information available to me in this graph. pH decreases when H+ increases. So as I go this way, I see a lower pH. These brackets mean concentration. And then by example, we can look at how to use how a relationship between concentration, as long as that concentration has a 1 in front of it, that the negative exponent changes its sign and becomes the whole number 1, that the -4 changes its sign and becomes the whole number 4. So that's the relationship between the molar concentration of H+ or H3O+ and pH. So we can do another example where if this was suddenly, instead of 1, it was 11, what would the pH be? It would be 11, so the relationship does not change as the numbers get bigger. We maintain that. And then we have this. What if we said the pH instead of saying the concentration? Could we figure out the concentration? Sure, we would just work backwards. Like we would go from 4 to -4. So that would mean that I would have this concentration in molarity. There you go. So the units would be molar. And finally, a neutral solution has a pH of 7. So remember, that tells me that I have 10 to the -7, or 1 times 10 to the -7 is equal to H+. And we had said that at a neutral solution, the two concentrations are the same. So these two are the same. But I'd really like you to think of it in terms of decimal points, because I think you have a better understanding of decimal points. And what that means is if the decimal point starts here, I've moved to the left and made it smaller by moving my decimal point 7 places, or dividing by 10 7 times. That would mean that there are 6 zeros in between the calculation. So you could go from a decimal number up to a exponent number, and that would be helpful. Now, when you take the H+ and OH- of a neutral solution of water, you multiply that and you get what's called Kw, or 1 times 10 to the 14. So it turns out that regardless of your acid or base solution, that formula holds all the time. That no matter what, as the H+ increases and increases, then my OH would go down, and they would go down, up and down in such a way as to still equal this number. And vice versa, maybe OH goes up and my H+ goes down, and again, the result would be the same product. 1 times 10 to the 14. So we're going to use that in this to find OH in this relationship. So here's what we've already done before. We've already gone from pH of 3 to a concentration of 10 to the minus 3 molar. And now what I need to do is we're going to use this formula. And I have 10, or 1 times 10 to the negative 3 times 1 times 10 to the what? I don't know what it is. I do know it's negative. And that's equal to 1 times 10 to the minus 14. So what I'll have to do is I'm going to look at just the exponents. And the way it works is that if you just use the exponents, it's going to be minus 3 plus x, or what, equals minus 14. And so the result is 11. So I'm going to get 11 here. I can't see that. 11. And then there's another relationship down here that we haven't looked at before. And that is pH and POH equals 14. So we'll work that one out right here. So pH plus POH equals 14. And my numbers are 3 plus x, I don't know what POH is, equals 14. And so x would be 3 plus what equals 14? X would be 11. So you can see that the relationship is the same as we saw with pH. That pH gives me 3 and an exponent of negative 3, and POH gives me 11 and a negative exponent of 11, right? So there we go. For the base solution, be nice if you figure this out, so pause the video, give it a shot. But you do have 2 more to do on the lecture notes. So let's first go this way. Let me undo this so we only are thinking about one thing. I'm going to go over here. What would that be? Remember, they add up to negative 14, so this will be negative 5. Remember that these are connected, so I can just bring this down and change its sign to make it 5. And then we're going to use the same formula we just used up above. We have that, and now we know POH is 5. And we're going to solve for H, so that makes it 9. And we can check that. Here's our 2 H values, and we can see that we could have just got pH from H+, which maybe that's the easiest way to do it. Quick math note, sometimes, like in these up here, the 1 gets dropped, and that's because 10 to the minus 5 is identical to 1 times 10 to the negative 5. And a common mistake is when I say pH of 5, I do have people who put a 5 here sometimes. So be careful of that. Okay, that's it. That's the end of the lecture. So I hope you get all the notes and can fill them in. Thanks. Bye.